Welcome to Git Good. This is my introduction to Git and GitHub for absolute beginners. In this presentation, I'm going to be explaining the absolute basics of what is Git and how does it work on a very basic level. This presentation is intended for people who basically, I will assume that you have no knowledge of Git whatsoever, and to a certain extent, no knowledge of even what a software project is. If you've never used Git before, maybe you've heard of it and you're curious about it, or maybe you are using it, but in a very sort of surface level way, like you're on a team that uses Git and they've given you the commands that you're supposed to put into the terminal and you're dutifully copy pasting them, but you have no idea what they mean. A lot of people start out that way. This presentation is for you. You may be here as someone who is using Git and is actually fairly confident with how to use it and what the basic concepts are. This presentation may be interesting and maybe slightly illuminating to you. Maybe you'll learn some things you didn't already know. If you consider yourself someone who already solidly knows how Git works on a deep level, thanks for coming. Thanks for being curious about the presentation. But I will warn you that this may be a presentation where you have some feelings of frustration. Why isn't he mentioning this? Why did he explain something in this way? I'm going to be glossing over certain things. I'm going to be simplifying certain things for the purposes of a more beginner-friendly explanation. And there's certain things that I'm going to just be lying about completely for the sake of simplicity. So bear with me here. I will come back at the end and briefly touch on the things that I have lied about or not mentioned. But this is really intended for absolute beginners, like it says in the title. So without further ado, let's jump into it. So what is Git? Well, Git is not an acronym. The origin of the name Git is from the British slang term that basically refers to, a stupid or unpleasant person. A self-deprecating joke from the creator of Git, Linus Torvalds. He is also the creator of the Linux kernel. And so the story goes, the possibly somewhat mythical story, he was so fed up with having to talk with and communicate with people that he created Git so that he could collaborate with them on Linux without actually having to exchange words with them. And he calls it Git because he's being a Git. The story is slightly more complicated than that, but suffice to say that on a very basic level, the very first answer that you give if someone asks what is Git is an application for collaborating with other people on software projects. It does other things, it has other functions, but this is basically what it is for and what it was invented for. And I think it's useful to spend a little bit of time just understanding what a software project is, because that will help us actually motivate the existence of Git and understand why it was created. So let's talk about software projects. What's a software project? Well, as far as Git is concerned, a software project is exactly one folder, also called a directory. Those words mean the same thing. One folder or directory with some files in it, and potentially some more subfolders or subdirectories inside it, which can in turn have files, and so on and so forth. There's lots of other concepts that go into software development as a process. So the initiative to create or maintain some software will involve more than this. There's CI/CD pipelines, and there's end-to-end tests, and release artifacts and all that kind of thing. But setting aside all of that, as far as Git is concerned, this is what a software project is. It's just a folder with some files in it. Now, what do I mean when I say files? Well, in principle, the folder can have any kind of file in it whatsoever. But typically in software development, we use something called a plain text file. And a plain text file is basically a file. It's a piece of data in a file system that has a string of characters in it and nothing else. Those characters are letters and symbols and spaces, and they do not have any formatting. So they don't have font, they don't have color, they don't have size or anything like that. Why do we use files like this? Well, it's because of cross-compatibility. When you open up a plain text file in a plain text editor, you know that you're looking at the exact same characters as anyone else who opens up that file in some other text editor. And you can configure your text editor to show you that text in any formatting you want. But when that file is eventually fed into some software to process it, like, for example, if it's computer code and you want to compile it, stuff like formatting, size, font, none of that is relevant to compiler. It's not relevant to a machine that might be reading these files. It's not typically relevant when the purpose of the files is to specify something or to program something. So we use plain text files because they're the simplest possible thing that can encode the information that we want in a software project, which is words, computer code, and that kind of thing. Like I said, you could put any type of file you want into these folders, and Git would very happily save versions of those files, and you could do all of that, but it's sort of optimized for this specific use case with plain text. Now, what am I talking about with that use case? We've talked about what a software project is, but what does it mean to collaborate on a software project? We're going to imagine a toy scenario with two characters, Alice and Bob. They're working on a software project together, and we're going to assume that they're doing it in the most naive possible way. So we're going to assume Git doesn't exist, and we're going to assume that Alice and Bob have not heard of any methods for collaborating on software before. And hopefully, as we walk through this demo example, we'll notice the problems and the inefficiencies that sort of would motivate someone to invent a version control system like Git. So here's Alice and Bob. Alice is working on a software project. She's called it Alice's project. And like I said before, a software project is just a folder. And in this case, that folder has two files in it. Now her friend Bob wants to help her work on that project. And so what she does is she just takes that folder with the files in it and she zips it into a zip archive and she emails it to Bob, and then Bob receives it and he unzips it onto his computer. And so now we have Alice and Bob with their own separate computers with two separate and identical copies of the same software project. Now Bob goes ahead and he starts making some changes because that's what he wanted to help out with. Alice can't do all of the work on her own. And so Bob is going to go in and make some changes. And now that he's made those changes, we can see that these two copies of the same software project are different. There are changes that exist in Bob's copy of the software project that don't exist in Alice's copy. But we want the copies to always be the same so that we're working on the same project. So what he does is he can take his copy of Alice's project and zip it into an archive and email it back to Alice. And then Alice can unzip it. And now she has two copies of the same project on her computer. And she can see that she can just go through and find the differences. So she'll compare the two different files. She'll compare in one folder to readme.md in the other folder and notice, here, look, there's a change here. There's some extra text. I'll copy that over. And then she can go through the two copies of main.py and see, there's a change here. I'll copy that over. And then once she's done that, she has, once again, two identical copies of the project, and they are also identical to the copy that Bob has. And so she can, delete one of them and happily keep working on the project. But you'll notice that might be a lot of work to do, especially if there's a lot of changes. Like, let's say Bob makes some changes on these files every day. That means Alice needs to go through and find all of the changes and apply them to her copy of the project every day. And it also means that she needs to keep Bob up to date with all of her changes. And then this gets even worse when we add a third collaborator. Let's say Carol enters the picture, and now all three of them are working on the software project. And now they need to send all of the changes that they're making to the other two. And those other two need to be sending their changes back. And mistakes are going to get made, time is wasted, and a bad time is had by all. So let's see if we can imagine a better way of doing this. I'm going to talk about Git collaboration in a nutshell. And this is going to be our first pass at sort of walking through how Git collaboration works. I'm going to come back to this process and expand on it. So just know that this is hugely simplified, but I will be going into more detail in this presentation. So let's say that Alice has her software project, her copy of the project on her computer, and she pushes it. We'll use that word because that is the word that is used. She pushes it to a central server that all three of them have access to. So now she has a copy on her computer, and the server has a copy, and those copies are the same. But the copy that is on the server is sort of the authoritative one. That's the copy that is their single source of truth for what the state of the project is. So now Bob and Carol can then clone that project down from the server. And again, clone is the word that we use here. And now all three of Alice, Bob, and Carol have copies of the software project on their computers that all match the central shared version. For simplicity's sake, I'm not showing the contents of these files anymore, but we'll just assume that there are some contents here. And what we're going to do is we're going to imagine that as Alice, Bob, and Carol start making changes, we can visually track those changes with these different colored blocks. So let's say a green block means that you added something to this file in a specific place. A red block means that you deleted something from the file in this specific case. And no blocks means you didn't change that file. So Alice, Bob, and Carol go ahead and they start making some changes. Alice has added a bunch of things to both files. Bob has added and removed from one of the files. And Carol has just removed something from one of the files. So now what happens? So Alice is the first one to finish her changes. So she pushes her changes to the central authoritative version of the project. And now the server has all of her changes on it. And so the server matches what her version of the project looks like. Now what Bob can do is before applying his changes, he can then pull all of the changes that were tracked by the central version of this project. He can pull those changes down to his copy of the project. So now in his copy of the project, he has all of the changes that Alice made, and he also has the 2 changes that he made. So now what he can do is he can push his changes up to the server, and the server notices, your copy already has these changes that I know about, but it also has these 2 other changes that I don't know about yet. And so it can then add just his changes to the central copy of the project. And now the central version of the project matches what Bob has on his computer. And meanwhile, Carol will then pull down the changes from the central version. She's pulling down the changes that Alice created and the changes that Bob created. And now her copy of the project is the most up to date. It has the changes from all 3 collaborators. And what she can then do is she can push her changes back up to the central server. And now the central server has all of the changes from all 3 collaborators. And Alice and Bob, who don't have the changes from the next person down the line, can now pull from the central server. And the central server will notice, I know about all these changes. You have some of those changes, but you don't have all of them. So I'll send you those changes you don't have. And so when you pull, you get all of the information that was tracked, all of the changes that were tracked by the central server, and you get yourself up to date. And now all 3 of these lovely characters have exactly the same state of the project on their local computers, thanks to the central copy that was tracking every change that occurred. Now, if you were just curious about what Git is and basically how it works, but you don't actually need to use it day to day, this is a perfectly good explanation, I think. Some people might disagree with me, but if I was explaining this to my non-technical friends who don't work in software, I think this would suffice as an explanation. But if you were to move forward with only this understanding of how it works and try to use Git actually on a team that uses Git, you would quickly find that you're missing some critical information that you need to do basic things. So we're going to talk about branching. And to do that, we're actually going to expand on what Git software project actually looks like. We're going to add some levels of detail here. So we're going to zoom in just on Alice. And Alice has a software project. That's this outside yellow folder and the 2 files that you're familiar with. But because this is a Git software project, every software project that is using Git also has a special folder inside of it. It's always called .git, and .git is what makes this a Git software project. And this folder here, the one that's called .git, is called a repository. So you have a software project, you have a copy of a software project on your computer, and inside of that project is a special directory. It's called .git, and it's your Git repository. Now, what's in a repository? Well, a repository contains a snapshot of every file in the software project at every stage of development. So every version of those files that's ever existed, the repository has a snapshot in time of what those files looked like. Every time you make a change to one of these files and you basically save it, you commit it to the repository, you create a new snapshot, and that snapshot is saved forever. Now, one of the benefits that you get from this is that Git tracks the state of your project over time. And so just like you can do in, for example, Google Docs, you can open up the version history of a file that you're looking at. You get that functionality from Git. If, let's say, you're working on a project and you change some things and you think to yourself, oh, geez, I think I deleted something a couple changes ago that I didn't mean to delete. You can actually look, you can inspect any of these previous versions of the files, and you can see exactly what they looked like at any given time. And if you were working on your own, Git would actually be a great way of tracking changes like that, even if you weren't collaborating. The reason it does this functionality is somewhat accidental. It does them so that it can actually coordinate and track those changes for the sake of sharing them among collaborators. So I'm going to simplify those snapshots and down to just blobs in this diagram so that I can show you the actual data structure of what's inside the Git repository. Each one of these snapshots has a pointer, so it's basically a reference that points at its immediate predecessor in the chain. So you end up forming this linear timeline with the arrows pointing backwards as a convention in Git diagrams. It's a little bit confusing because the arrows point backwards in time, but I'm doing it here because you will see diagrams like this on the internet and the arrows always point backwards in time. And so I don't want you to be confused later when I'm not there to explain it. So the arrows point backwards in time. Each commit in the chain knows its immediate predecessor, which means that Git can take any given commit and it can figure out what did this look like exactly before this commit. And what happens when you make a new commit, we call this committing. Git basically just takes a snapshot of all of the files, it puts that snapshot into .git, and then it creates a pointer that points back to the snapshot that you used to be on. I'm going to be using snapshot and commit somewhat interchangeably in this presentation. That's because for our purposes at this level of understanding, they're basically the same thing. You will see them referred to as different things because they are in fact different things. And if you are already a Git expert, I'm sorry, that's probably going to drive you crazy, but it is the way it is. Now, how do we know which of these is the most recent version? Well, Git has another object in the repository, which is called a branch. And a branch is basically just a label which points at a certain commit. Every Git repository comes with a default branch already in it. This is sometimes called the main branch. It's sometimes called the master branch. You will see those used somewhat interchangeably. Main is the more modern one that a lot of teams are switching over to for inclusivity reasons. You will see it called master, but in principle, it can be called anything you want. It can be called unicorn or butterfly or whatever you want to call it. The name of the branch is totally arbitrary and user defined. They all have to be different from each other, but what it does is it just points to a certain commit, and that commit is usually the most recent one on the chain. And so then what happens is when you make a new commit, it adds a new commit in the chain and it moves the branch pointer over to point at that more recent commit. Now, why do we call them branches? You may have guessed it's because your timeline might not actually be linear. So you might have versions of the software project that sort of diverge. So we had here the state of the project at C4, and then a change was made on the main branch, diverging from C4, and then a different change was made on the feature branch, diverging onto a different branch of this tree, also from C4. So C5 has a predecessor, which is C4, and C7 has a predecessor, which is C4. And those continue forward in time. And the branch basically points at any commit along the line, which is to be the place where you put the next commit. So what that looks like, if I were to make a new commit onto the main branch, I would extend that branch and move the pointer out by one step. And if I were to make a commit on the feature branch, I would move that along and extend that branch by one commit. And then eventually, you'll want to bring the changes from one branch and the changes from another branch all into one commit. And when we do that, it's called a merge. So in this case, if we are merging the feature branch into main or main into feature, it doesn't matter right now. We end up with one commit that has two predecessors, this C11 commit has a predecessor of C9 and a predecessor of C10. And what Git has done is it's found all of the changes that accrued over this branch and all of the changes that built up over this branch, and it just applies them all to C4, and you get C11. And then the main branch moves along with it. Now, let's apply this level of detail to Alice, Bob, and Carol. So now we can see that they have their 3 copies of the software project. Each of them has a copy of the repository as well inside their project directory. And that repository has all of the commits in the branching structure that they exist. And those match the central repository. And now we can actually see the reason why we call the thing that is on GitHub a repository is because it's just the repository folder, but not with the surrounding project folder. Because no work is actually being done on this server. This is a server. It doesn't have your text editor running on it. And so all we have is what we've color-coded with gray, the Git repository in the central server, whereas that repository is inside the project folder on the individual user's computers. So now what happens when these actors make some changes? Let's say Alice makes a change on this branch, Bob makes a change on this branch, and Carol makes a change on this branch. The benefit we get from this branching structure is that all 3 of them can push their changes to the central repository, and we don't need to worry about how those changes conflict with each other as long as Alice, Bob, and Carol are working on separate branches. Because the way these workflows typically happen is that we make lots of commits in a given day. A commit is meant to be a very cheap operation that you do all the time. And so if we were doing that all the time and then always had to negotiate how those changes might or might not conflict with each other, that would get somewhat unwieldy. So what we typically do is we work on separate branches, and then when we push and pull to the central server, we don't really need to worry about all the changes that the other users aren't making until it's time to merge. So we stay on our own branch, and it's purely additive. We just add a new commit to our branch, and that can move forward in time and basically ignore the changes that are coming from other users. At this point, if this were a closed source project where only trusted individuals were working on the project, this is all we would need. But in fact, in open source software development, you may have changes coming in from people you don't know. So what happens when a 4th party comes in named Derek? And Alice, Bob, and Carol, they don't know Derek. Derek is a stranger. They don't know what his intentions are. They don't know whether he wants to actually help with the project or if he wants to vandalize it or sabotage it in some way. Well, this is where a platform like GitHub comes in. This is the service that most software projects use. GitHub has a feature called a pull request, which we're going to talk about now. So let's look at what that looks like. Alice has her copy of the software project. She has a GitHub repo under her account. Now, what Derek can do is he can do an operation called a fork. He makes a copy of it under his account. So this version of the repo is under Alice's GitHub account, and this version is under Derek's GitHub account. And Derek does not have access to push any changes to Alice's version of this project, and Alice doesn't have any access to push any changes to Derek's version of the project. And what this means is that Alice is basically safe from any potential bad changes that Derek might want to make, because Derek can then clone his version of the repository, his fork of the repository down to his computer. He can make all of the commits that he wants. He can push those up to his version of the repository. And Alice is completely insulated from any changes that Derek made, whether they were malicious or incompetent or perfectly fine. But what happens if those changes were good changes in good faith and Derek wants to charitably give those changes back to the repository that he forked from? Well, what he can do is he can open up something called a pull request, which is something that lives purely inside of GitHub. It doesn't exist anywhere on the local machines. And the pull request basically says, hey, I've got this commit or string of commits, and I think you should add this to the project. And what Alice can do is she can survey that pull request. She can see what the changes are. She can see if they're good. And if she approves of them, she can commit those. She can merge those changes into her repository. And that way she has total control over what changes are coming in from people that she doesn't necessarily trust. So that basically sums up my explanation of how Git works and what the different bits of terminology mean. But I'm going to walk through a concrete example of this. So here I've got a folder. It's called Git Gud. It's a folder called Git Gud. I've made 2 files in here, and here you can see what those files are. One of them is a README file, one of them's a Python file, and those are existing here on my desktop. And over here you can see a diagram explaining in the visual terms that we saw previously. So this, it could conceivably be a software project, but it is not yet a GitHub tracked project. It doesn't have a repository inside it. So what I do is I open up the terminal and I run git init, stands for initialize, and the Git application basically just creates an empty Git repository inside my project. So now you can see that here. You can see it comes with a default branch. In this case, the branch is main. You can see it says that here. But it doesn't have any commits in it yet. So this is just an empty Git repository. It doesn't have any snapshots of my files. So now when I run git stage and git commit, don't worry about what stage means. I run git commit and I put in a commit message. A commit message, it can be anything, but it should be something that usefully describes what the changes are that you're making. I run git commit, and Git basically just takes a picture of all of the files that exist in the parent of the Git repository, and it puts that snapshot into the repository. But this is all just on my local computer. None of this is on GitHub yet. So now what I do is I go to the GitHub website, I log in, I click new repository, I fill in all the information of what my repository should be called, and I create it, and then from my computer, I push my local repository up to the repository that I created on GitHub. So now you can see I'm running git push -u origin main. Don't worry about that, what that means, but notice I just said git push. So I'm pushing the commit that I have in my local repository, I'm pushing it up into the Git repository. We can see on my local computer, I've got the files here. You can see those files are here, and I've got the Git repository here. In the diagram, this is the Git repository, and inside that repository is a snapshot of these same files. And this repository exists in a duplicate form on GitHub, which you can see here. And we can also see that when I go to the GitHub website, I can go to the homepage of my repository. There you can see the name. And here you can see the 2 files that I pushed up here. Here's the README and here's the hello world.py. And you can see the commit message that I wrote. It just says my first commit. This commit message is telling you what was the commit message on the most recent commit that changed this file. And there's only one commit so far. It's the first one. And so there's the commit message you can see there. And what GitHub also does is if you have a file called README, it will take that file and it will display it on the homepage. So here you can see that, is that what I wrote? Yeah, so here you can see the contents of the README that I wrote here. Git is displaying that README on the homepage. So whatever you write in the README is what it will show on the homepage of this repository. Now what happens when I go in, I open up the README, I change it, I add 2 more lines to it, and then I run git commit -m with a new commit message, added 2 more lines to the README. And what's happened is Git has snapshotted those 2 files, and it's put that snapshot into the Git repository. It's snapshotted both of them, even though I only changed 1. But those changes only exist on my local computer so far. So now I have to go into the terminal and run git push, and the new commit that I created is pushed up to the central repository. And now the central repository, the GitHub repository, matches my local repository, which you can see here. So now you can see on the next to the README file, you can see that last commit message, which is the last one that changed it, and you can see the updated text on the homepage. And that is basically how Git and GitHub work for absolute beginners. What did we talk about today? So we talked about files and directories, which are also called folders. We talked about a software project and how, for the purposes of Git, a software project is it's just a folder with some files in it. We talked about snapshots and commits. Those are technically two different things, but they correspond with each other one-to-one. So for this basic explanation, they are essentially the same thing. We talked about repositories. A repository is basically a special folder with snapshots of every version of software project in it. We talked about branches. Those are the sort of branching structures inside of a repository so that different versions of the software can exist from the same predecessor. And we talked about pull requests, which is how we safely include changes from untrusted parties on GitHub into our project. We also learned some Git-specific verbs. So these are commands that are used in Git: commit, merge, push, pull, clone, and fork. There's a few things that I glossed over. These are things that I encourage you to look into in your own time. I didn't talk about the head pointer. That is important for understanding certain errors that you might encounter, or certain advanced, well, not necessarily advanced, but maybe like mid-level things that you need to do in Git. There's different ways of merging two commits. There's a three-way merge and a fast-forward merge. I didn't talk about that. I didn't talk about the difference between merging and rebasing. That's a whole thing. It's one of those arguments that will never end. I didn't talk about tags. I didn't talk about what a remote branch is. I didn't talk about the distinction between a commit and a snapshot, like I mentioned before. That's my presentation. Thanks for watching. And if you have any questions or comments or feedback, we'd love to hear from you. Thank you.